Hi, my name is Ikin and we're presenting about the introduction. And for this project, we are tasked to design a plant producing methanol utilizing the conventional syngas route. And we select this specific pathway due to its low carbon potential and high technological maturity. And methanol is a crucial platform chemical serving as an essential feedstock for producing formaldehyde, acetic acid, and also some synthetic fuels. And to establish a stable simulation baseline, we simplify our reaction network to focus strictly on the direct hydrogenation of carbon monoxide into methanol. Looking at the reaction kinetics, our main equation in this reversible reaction of 1 mole of CO reacting with 2 moles of hydrogen to form methanol. This takes place over a commercial solid copper zinc alumina catalyst. We utilized the well-established Gulf kinetic models from 1988. Crucially, we even applied an effective factor to our model to account for internal pore diffusion resistance inside the solid catalyst pellets, which prevents unrealistic overconversion in our simulation. As for the reactor type selection, we selected multi-tubular packed bed reactor, or which we know as PBR in short form, which is analogous to the industrial logic isothermal reactor. We roll out a CSTR because it is entirely unstable for high pressure and pure gas phase applications. We also avoid using a fluidized bed reactor because pushing gas at high velocity will cause severe physical attrition and essentially destroying our catalyst pellets due to high temperature. Meanwhile, for our operating condition, we operate this at temperature of 220 degrees Celsius and also high pressure at 7,000 kPa at a massive industrial feed rate of 20,000 kilomoles per hour. And we managed to achieve a controlled single pass conversion of 0.28. And let me explain exactly how we optimize these parameters. First, looking at the effect of temperature on conversion. As temperature increases from 200 to 220 degrees Celsius, the kinetic reaction rate speeds up as in and increasing the conversion. However, because methanol synthesis is highly exothermic, pushing the temperature beyond 220 degrees causes the equilibrium to shift backward towards the reactants. Therefore, 220 degrees is our optimal thermodynamic sweet spot. Next is the effect of pressure. According to Le Chatelier principle, because our reaction consumes 3 moles of reactant gas to produce 1 mole of product gas, higher pressure will strongly shift the equilibrium forward towards the methanol product formation. This decrease in total moles is the driving force behind our selection of a high 7,000 kPa operating pressure. Meanwhile, when we analyze the syngas feed rate, we actually observe a clear inverse relationship compared to previous. As the feed rate increases, the overall conversion drops. This happens because forcing more gas through the reactor shortens the contact time between syngas and the solid catalyst, which reduce the reaction rate. Lastly, and for my part, is residence time. And to summarize that behavior mathematically, we will look at this specific residence time plot, or what we know as tau, which equals to a reactor volume divided by the volumetric flow rate. And a higher feed rate directly results in a lower residence times. In conclusion, because we are pushing a massive 20,000 kilomoles per hour through the reactor, the gas simply doesn't have enough contact time to reach full equilibrium. This explains our intentional single conversion limit to 0.28 only, which perfectly tees up with my partner, Kaisa, to discuss the physical sizing of the reactor.
Hello everyone, my name is Tan Kai Sang from Chemical Engineering course and I'll be presenting the reaction engineering regarding the reactor design and the production capacity of our system. And now I'll be explaining the Levin spill plot that we achieved from our system. The Levin spill plot shows that FA naught over the reaction rate increases along with the conversion rate, meaning that the reaction rate decreases along the reactor as reactant are consumed. Therefore, achieving a higher conversion rate requires a larger reactor volume. And now I'll be explaining the Simpson 5-point rule that is used to estimate the reactor volume from the Levin spill plot. By using Simpson 5-point rule at a conversion rate of 28% under operating condition of 220 degrees Celsius and 7,000 kilopascal, the reactor volume is calculated to be 12.57 cubic meter. This means that 12.57 cubic meter is the minimum volume required for a PBR to undergo the reaction. As the reactor we are using is a packed bed reactor, which is a PBR, thus we are using catalyst. Due to the existence of catalyst particle that cannot fully fill up the reactor, so void space exists for fluid flows or gaseous flows, depends on what is the reaction going on and what is the product that is produced from the reaction. So therefore there exists a void fraction of 0.45 in our PBR reactor. Thus by doing some calculation using that void fraction of 0.45, we will achieve an actual reactor volume of 22.85 cubic meter. For the volume of the reactor design, there actually exists a slight deviation between the reactor volume we defined in the simulation app and the volume we calculated through the Levin spill plot. Because simulation consider real operating conditions that are not included in the ideal calculation of the Levin spill plot. And now I'll be explaining the cause of deviation between the volume obtained through Levin spill and the volume we defined in the simulation app. This deviation is expected because the Levin spill method assumes ideal conditions such as plug flow, no pressure drop, and constant properties. But in a real-life packed bed reactor, pressure decreases along the bed, reducing reaction rate and increasing the volume. Additionally, only part of the reactor contains catalyst due to the void fraction, and the heat effect due to the reaction can influence the reaction performance, either increasing or decreasing the reaction rate. On the other hand, while in industrial practice, reactor is also designed to be larger to provide a safety margin and ensure a stable operation. This larger volume from simulation is realistic and acceptable. And now I'll be discussing about the production capacity from our proposed system. With a syngas feed rate of 20,000 kilomole per hour and carbon monoxide making out about 33%, applying a conversion of 28% give a methanol production rate of 1,848 kilomole per hour. This corresponds to about 468,000 tons of methanol produced per year, which is within the industrial production scale. And now we'll be talking about the actual production capacity, which is different from the last slide. While last slide we are talking about the ideal production capacity, where if they assume if everything goes on well, we'll get that amount of methanol production rate. While in reality, the actual production may be lower due to factors such as catalyst deactivation, pressure drop, temperature variation, maintenance downtime, and feed fluctuations. To account these uncertainties, reactors are designed larger to ensure reliable and continuous operation to get as close as the ideal amount that is planned to produce. So the picture on the left side is the proposed PBR reactor stream. And to sum this up, the packed bed reactor operates at 220 degrees Celsius, 7,000 kilopascal with a conversion rate of 0.28, which is a 28% per pass. This calculated reactor volume is 22.85 cubic meter, while the simulation gave 30 cubic meter due to real operating effects. Overall, the design is consistent with industrial practice and support large-scale methanol production even under an actual production capacity. That's all for my part. Thank you.
Hi, my name is Ada Shakira, and now I will be presenting the separation process for methanol purification. So first, we need to identify the species and impurities present in the system. From the PBR outlet stream, the main components are hydrogen, carbon monoxide, methanol, and a small amount of water. Hydrogen is the dominant component at about 61.62%, followed by carbon monoxide at 27.03% and methanol at 11.34%. After passing through the flash drum, most of the light gases are separated and recycled, while methanol condenses into the liquid phase. However, the crude methanol stream still contains impurities. As shown, the methanol is about 98.9%, while there is still small amount of hydrogen, carbon monoxide, and water present. These impurities remain due to their partial solubility in the liquid phase, so additional purification is required. To achieve the required methanol purity of 99.5%, an adsorption-based purification unit is used after the flash drum. As shown here, adsorption acts as the final polishing step to remove the remaining impurities. The crude methanol stream enters the adsorption unit around 30 degrees Celsius and 27.11 kilopascal with a flow rate of 1.873 times 10 to the power of 5 kilograms per hour. Adsorption is selected because it is highly effective for removing low concentration impurities such as water and dissolved gases. It also does not require phase change, which results in lower energy consumption compared to distillation. In addition, adsorption is more efficient for final purification, especially when dealing with trace of impurities. To add, a molecular sieve is used as the absorbent due to its high selectivity for water. Therefore, this adsorption unit ensures that the final methanol product achieves 99.5% purity.
From the simulation results, the crude methanol stream contains about 98.9% methanol with impurities, such as hydrogen, carbon monoxide, and also water. But among these impurities, water is identified as the most critical purity because it interacts with our methanol and affects the product purity. To achieve a required 99.5% purity, we use molecular sieve, specifically zeolite, as our adsorbent. This is because it has a process of 3 angstrom, which only allows water to pass through and be absorbed, while exclude a larger methanol molecules, minimizing our product loss. In addition, molecular sieve has high surface area, fast adsorption kinetics, and excellent thermal stability, making them suitable for continuous industrial operation. Therefore, molecular sieve is the most suitable adsorbent for this system. To analyze the absorption behavior of water on the molecular sieve, two isotope models are chosen, which are Langmuir and also Friendlich isotope. This model help to describe the relationship between equilibrium concentration and also of the impurity and also the absorption capacity of the absorbent. So, the Langmuir model assumes monolayer adsorption on a uniform surface, while Friendlich model describes adsorption on a heterogeneous surface with different energy sites. From the result obtained, the Langmuir model show a high correlation, which are the R squared value is 0.99, indicate a good fit. However, the Friendlich model provides a slightly higher R squared value, which is 0.997, which means it represents the adsorption data more accurately. This suggests that the adsorption process occurs on a heterogeneous surface, which is more consistent with the structure of a molecular sieve. Therefore, Friendlich isotope is the one that we selected as the most suitable model, and it is also in the subsequent absorption mass calculation.
Next, the amount of adsorbent required is calculated using mass balance and the Friendlich isotope model. First, we determine the amount of water to be removed. Based on the crude methanol composition, the water mole fraction is 0.0017. Using the total flow rate of 5,882 kmol per hour, the molar flow rate of water is calculated as molar flow rate of H2O equals to 0.0017 times to the 5,882, which gives 10 kmol per hour. This is then converted to mass flow rate using molecular weight of water, which is 10 times 18, giving 180 kilograms per hour. Next, the absorption capacity is determined using the Freundlich isotherm. From the graph, the constants are K equals to 1.239 and N equals to 1.67, giving the equation QE equals to 1.239 CE to the power of 0.5992. Substituting the concentration, the absorption capacity is calculated as 0.02 kilograms of water per kilogram of adsorbent. Finally, the adsorbent mass is calculated using M equals to mass flow rate of H2O divided by QE. This gives mass equals to 180 divided by 0.074, which equals to 6,569 kilograms of adsorbent is required.
Now, I will explain the absorption column design used in this process. A continuous fixed bed absorption column is selected to remove impurities such as water, carbon dioxide, and trace gases from the methanol stream. This type of column is widely used because it is simple, stable, and suitable for high pressure operation. To ensure continuous operation, a multi-column system is applied. While one column is performing absorption, the other column undergoes regeneration. This allows the process to run without interruption. The column is packed with an absorption material such as molecular sieve, which provide a large surface area for mass transfer. The gas stream flows upward through the packed bed at high pressure around 7,000 kPa after cooling. In terms of design, the column diameter must be large due to high flow rate of about 200,000 kmol per hour. The bed height is designed to be higher than the mass transfer zone to ensure complete removal of impurities. As the absorption process continues, breakthrough will occur when impurities start appearing at the outlet. Therefore, the column is switched before breakthrough to maintain methanol purity at 99.5%. To support the design, a preliminary sizing is carried out. A superficial velocity of 0.2 meters per second is selected to balance pressure drop and contact time. The column area is estimated using the equation A equals Q over V. A higher flow rate results in a larger column diameter to maintain stable flow. For regeneration, pressure swing absorption is selected. This method is suitable because the system already operates at high pressure and require lower energy compared to thermal regeneration. The regeneration cycle consists of four steps. First, absorption at high pressure. Second, depressurization depressurization to release impurity. Third, purge gas is used to remove remaining impurity. Finally, repressurization prepares the column for the next cycle. With the use of multiple columns, the system can operate continuously while maintaining high purification efficiency.
Now, the overall purification system consists of three main stages, which are the flash separation, adsorption, and final polishing, which each stage plays an important role in improving our methanol purity progressively. First stage is the flash separator, which removes most of the hydrogen and carbon monoxide based on the volatility differences. At this stage, the methanol purity reaches about 98.9% with approximately 1.1% impurities remaining. However, some gases and water remain dissolved due to high pressure, so further purification is needed in our second stage, which is the adsorption. Adsorption is used to remove water, which is the most critical impurity. From the calculation, the water flow rate is reduced from 10 km per hour to 1 km per hour, assuming 90% removal efficiency. This show that adsorption is very effective, especially for removing polar impurities like water. In the final polishing stage, the remaining impurities are further reduced about 99%. This result is a final methanol purity approximately of 99.99%, which actually exceeds the industrial requirement of 99.5%. But although this is an ideal simulation result, it shows that the system has strong safety margin. Overall, the multi-stage separation is highly effective. The flash separator removes our bulk gas, exhaustion remove water and trace impurities, and the polishing stage ensure very high purity. This approach reduces energy consumption as well, compared to distillation, and that reflects real industrial practice. Therefore, the system successfully achieved and exceed the required methanol purity of 99.5%.
Overall, the absorption system is able to purify methanol effectively by removing key impurities such as water and residual gases. The use of fixed bed multi-column configuration allows continuous operation while maintaining stable performance under high pressure conditions. The column design is suitable for handling the high flow rate from the reactor, ensuring efficient mass transfer and impurity removal. In addition, pressure swing adsorption enables efficient regeneration of the adsorbent with lower energy consumption. Therefore, the overall system is able to achieve the required methanol purity of 99.5% in a stable and efficient manner. Thank you. That's all from us.